Today, let's talk about a problem taken from the notorious Gaokao, or China's college entrance examination. This question comes from a particularly difficult 2003 math exam administered by the Jiangxu province. Around 520,000 candidates sat for the exam, with an average score of 68 out of 150. Needless to say, the difficult paper hasn't made for a pleasant experience for most of the candidates. In this video, the question we will be looking at was classified as one of the more difficult ones, but we will see that, with some proper thought before approaching the question, it is actually pretty manageable. Let's take a look at the question, the so-called flower bed problem. Given a flower bed, segmented into 6 different areas, and 4 flowers of different colors, how many ways are there to plant the flowers such that only flowers of one color are planted on each of the segments, and that no two segments touching each other could be planted with the same color of flowers? For example, if we have decided to plant red flowers in segment 4, none of the segments 1, 3, and 5 could be planted with red flowers, as they all border segment 4. When we are solving problems, it is always good to see if there's another way to represent and visualize the problem in a simpler way. In this case, we can actually represent each of the segments of the flower bed as a vertex denoted by the segment number, and draw a line connecting the vertices if they border each other. And we could further assign the vertices a color based on the color of flowers planted on that segment of the flower bed. The mathematical object which we have just created and described is called a graph, where the vertices connected by edges represent relationships between the vertices. A few immediate observations can be made from a graph. First of all, no vertices which are joined with an edge could have the same color. Since vertex 1 is connected to all the other vertices, this means no other vertices could have the same color as vertex 1. If we assume that the 4 colors were red, green, blue, and magenta, and color vertex 1 red, this means the vertices 2, 3, 4, 5, and 6 have to be colored using the 3 remaining colors of green, blue, and magenta. We can see that it is impossible for any 3 of these 5 vertices to share the same color, as this will invariably result in 2 neighboring vertices getting the same color. The only possible way to do this then is to assign 2 vertices the first color, and the other 2 vertices the second color, and finally the final vertex gets the third color all on its own. With this said, we can start doing the counting. First, we need to select the first 2 vertices of which we assign the first color. These vertices could not be connected with an edge, and 5 such pairs, namely 3, 5, 3, 6, 4, 6, 4, 2, and 5, 2 are available for our selection. In the diagram, you could see that we have selected the pair 5, 3 and colored it red, but it would have been the other pair 6, 3 as well. The second step would be to pick the second pair to be assigned a second color. Note that there are always 2 available choices regardless of our initial choice. For example, if we have started out with 5, 3, we could have chosen either 2, 4 or 6, 4 as our second pair. All other choices would have been impossible, as they will result in neighboring vertices being colored the same. Since the structure of the graph is symmetric, it doesn't matter which first and second pair we started out from. There are 5 choices for our initial pair, and 2 choices for the second pair. However, we need to account for repeats from double counting. We could have started out from 5, 3 as the first pair and assigned 2, 4 as the second pair, but we could have started from 2, 4 and assigned 5, 3 as the second pair as well. So a division by 2 is necessary to account for this double counting. After picking the pairs, it is finally time to assign them colors. There would be 4p2, or 12 ways to do so. We are basically picking 2 colors out of 4 to be assigned to the pairs chosen. In this case, arrangement matters, since the first pair being assigned red and second pair green is counted as a different scenario where the first pair is assigned green and second pair red. After this is done, we have two colors left, each to be assigned to vertex 1 and the final remaining vertex. This of course could be done in two ways, so we multiply the expression by 2 and obtain the final answer of 120, which is the right answer. So what do you think about the question? It is certainly not that difficult when we break it down like this, but do spare the candidates of year 2003 some sympathy, as this is only one of the many questions they have to work through in a very time-constrained exam. Anyway, I hope you have enjoyed the question, and I hope to see you in the next video.